c is the speed of light. Everyone knows that. It's the cosmic speed limit, the absolute maximum that exists. A barrier etched into the very fabric of the universe. That is wrong. Not just a minor error, a fundamental one. Here's the thing. The speed of light fundamentally isn't about light at all. Richard Feynman once said that if you think you understand quantum mechanics, you don't understand it. That wasn't humility. It was a warning. And that warning applies here. What most people think c is, it isn't. Gravitational waves travel at this speed. Electromagnetic fields update at this speed. The strong force holding atomic nuclei together? Same speed. Light travels at c because photons have no mass. But the limit doesn't belong to light. It belongs to the universe. c isn't just fast. It's the speed of causality. 299,792,458 meters per second. Not because someone decided it, but because the universe can't function any other way. It's the absolute fastest a cause can produce an effect. It's what stops the universe from contradicting itself. And in this video, we're going to walk through, one by one, the shockwaves that c creates. What happens to time when you approach c? What happens to space? What happens to mass? What happens to quantum mechanics, which seems to violate c in a way that kept Einstein up at night? What happens to the universe itself, expanding faster than light in certain regions? And at the end, the most profound revelation Feynman left behind. What light actually does at the quantum level, which completely rewrites what traveling at the speed of light even means. That's the final shatter. The most unexpected one. But let's start with the right question. What exactly is c? Forget for a second the image of a light beam shooting through a vacuum. That's just the representation, not the essence. Think of it this way. You're 150 million kilometers away from Earth. You're the sun. Suddenly, you vanish. You completely disappear. What does Earth feel first? The answer is nothing. For 8 minutes, Earth orbits normally, gravity intact, light arriving as usual. Then everything changes at once. The light vanishes, gravity disappears. Both travel at c. Both take the exact same time to get here. That's no coincidence. It's the exact same thing. c isn't the speed of electromagnetic light. It's the maximum speed at which any cause can produce any effect. Every massless particle travels at c. Every fundamental field in the universe propagates at c. Light, gravity, the strong force, they all play by the same fundamental rule. Feynman made this explicit. c governs information, not photons. It's the maximum speed at which the universe can update itself. The speed at which one event can affect another event somewhere else. Without this limit, cause and effect lose their meaning. You could send information into the past. You could shatter causality itself. And that changes everything. When you understand that c is the limit of causality, you see what's actually at stake every time c appears to be violated. This leaves us with a paradox that will echo until the very end of this video. If c is the limit of causality, what happens when quantum mechanics appears to transmit information instantaneously across any distance, completely ignoring any speed limit? Hold on to that question. The answer will change everything. But first, let's look at what c does to something you use every single day without realizing it. Let's talk about time. Here's what special relativity says, and what Einstein first proved mathematically in 1905. Time isn't universal. There's no cosmic clock ticking a now for everyone at the same moment. Depending on your speed, time flows differently for you than for someone standing still. The faster you move relative to a stationary observer, the slower time passes for you from their perspective. This is called time dilation. It's real, measurable, proven in multiple independent ways. Muons are particles created when cosmic rays hit Earth's upper atmosphere, about 15 kilometers up. They've got a very short lifespan, about 2 microseconds. At normal speeds, a muon would travel less than a kilometer in that time. It'd never reach the ground, but they do. Surface detectors register them constantly because they're traveling at nearly c. Their internal clock ticks slowly relative to us. To us, they live long enough to cross the entire atmosphere. This isn't just a theory. It's what detectors measure every single day. Then there's the twin paradox. One person leaves in a spaceship traveling at nearly the speed of light. The other stays on Earth. the traveler returns younger. It's not an illusion, not subjective perception. Their biological clock literally ticked slower. If you aged 30 years on Earth while your twin traveled near C, they'd return having aged only a few years. You'd be in completely different life stages, despite being born the same second. But where this gets real, where it actually affects your life, is GPS. When you open GPS on your phone, it triangulates with satellites in orbit. These satellites need incredibly precise clocks. The problem? They exist in two relativistic regimes simultaneously. Special relativity slows down their clocks. They're moving fast relative to us. General relativity speeds them up. They're further from Earth's gravity. These effects don't cancel out. Without relativistic correction, GPS clocks accumulate an error of about 38 microseconds per day. 38 microseconds sounds trivial, but GPS uses time to calculate position. So this error becomes almost 10 kilometers per day. 10 kilometers. Without relativistic correction, GPS fails in hours. The entire engineering of GPS quietly runs on special and general relativity. C breaks time, and we had to learn to fix it. Feynman always insisted on one thing: take the experimental results seriously, even when it offends common sense. Time dilation offends common sense. It's absolutely real. But time dilation has an even more disturbing sister. Time runs differently for moving observers, sure. But here's the kicker. Two events can be simultaneous for one observer and sequential for another. There's no universal now. Imagine two lightning bolts striking simultaneously at both ends of a train car. For someone standing on the platform, equidistant from the 2 points, the lightning strikes at the exact same time. Perfect. Now put a person inside the car, dead center, in motion. Light from both bolts travels at c relative to them always, no matter what. But they're moving toward one bolt and away from the other. So light from the front bolt arrives first. For them, the two bolts weren't simultaneous. One happened before the other. Who's right? Both of them. Simultaneity is relative. It depends on your frame of reference. No cosmic referee decides which is true. Each observer's version is equally valid. And here's what breaks physicists' intuition. Your now. All events happening at this moment in the universe is different from someone else's now if they're moving relative to you. Depending on their speed and direction, another person's now might include events that haven't happened for you yet, or happened long ago. This isn't metaphor, isn't poetry, it's geometry, pure mathematics. GPS corrections don't just compensate for time dilation, they account for the relativity of simultaneity between satellites in different orbits. The system works because engineers took this seriously. This is where C does something most physics books don't emphasize. Enter the light cone. Every event in spacetime has a past cone, everything that could have caused it, everything with time to reach here at C or slower, and a future cone, everything this event can affect at C or slower. Whatever's outside these cones is causally disconnected. You can't be the cause or effect of anything outside your light cone. C draws these cones. C defines what affects what. C is causality's geometry written into spacetime itself. Feynman once said, "Nature has no obligation to fit into human vocabulary." And it doesn't. Time and space? Broken. But the light cone itself, a boundary between what can and can't affect each other, implies something about the energy needed to traverse spacetime. That leads straight to what C does with matter. ERMC2. Everyone knows the equation. Most people don't understand what it actually says. It doesn't say mass converts into energy under special circumstances. It says mass is energy. Same thing. Same currency. A particle's rest mass is stored energy. C2 is the exchange rate. It's an absurd exchange rate. C2 is roughly 9 × 1016 square meters. S2. 1 kilogram of mass contains about 90 quadrillion joules of energy. To put that in perspective, the atomic bomb dropped on Hiroshima released energy equivalent to less than 1 gram of mass being completely converted. Less than 1 gram. And the destruction it caused. Stars work because EMC2 is real. In the sun's core, hydrogen fuses into helium. 4 protons in. 1 helium nucleus out. The helium weighs slightly less than those 4 protons. That mass difference, tiny but real, becomes energy. Repeat this on a colossal scale for billions of years. C2 is what makes the sun shine and warmed Earth for 4,500 million years. Now, why does this mean you can never reach C? When you accelerate something with mass, you're adding kinetic energy. As you approach C, the relativistic mass increases. You need more energy to keep accelerating. The object gets relativistically heavier, so you need even more energy. And more, and more. At exactly C, you'd need infinite energy. This isn't an engineering problem better tech can solve, it's a mathematical divergence. Impossible by definition. At the LHC in Geneva, protons reach 99,999% light speed. Their relativistic mass is about 7,000 times their rest mass. 7,000 times. For each proton, we inject energy equivalent to 7,000 times its rest mass just to reach that speed. Even then, we haven't reached C. We never will. C isn't a traffic limit. It's a mathematical singularity. Reaching C isn't forbidden like a law you could break. It's mathematically undefined for anything with mass. Mass and energy, two distinct concepts in classical physics, collapsed into one by relativity. C2 is the link. But if C governs matter, what happens when quantum mechanics doesn't seem to need C? When particles at any distance seem to communicate instantly? In 1935, Einstein, Podolsky, and Rosen published what became the EPR paradox, a critique of quantum mechanics. Einstein thought it was incomplete. There were hidden variables, he figured, information the theory didn't capture. If you knew these variables, the seemingly random quantum behavior would make sense within a classical local framework. Here's the problem. Quantum mechanics lets two particles be prepared in an entangled state. Measure 1, find spin-up. The other instantly collapses to spin down, no matter the distance. 1 meter. 1 billion light-years. Doesn't matter. Einstein called this spooky action at a distance, and he hated it. To him, no real influence could propagate instantly. There had to be a local, deterministic explanation. Today, labs around the world routinely generate entangled particles, fiber optics, photon experiments, quantum computers. Entanglement isn't philosophy. It's reproduced every week. That's why Einstein's question became urgent. If the phenomenon is reproducible, someone had to figure out what it meant. In 1964, John Bell did something extraordinary. He turned philosophy into math. Bell's theorem. If quantum correlations had a local explanation in hidden variables, they'd satisfy certain mathematical inequalities. If quantum mechanics was right, these inequalities would be violated. So it was testable. Einstein or quantum mechanics. John Clauser ran the first test in 1972. Alain Aspect refined it in 1981-82. In 2015, a loophole-free experiment settled it. Bell's inequalities are violated. Quantum mechanics wins. No local hidden variables. Entanglement is real. And now the ultimate tension. If entanglement is real and instantaneous, isn't C being violated? The answer is no. And understanding why means understanding the genius of the no communication theorem. Measure one entangled particle. You get a random result, spin up or down, 50-50. The other particle, wherever it is, instantly collapses into the opposite state, but you don't know it collapsed. From your perspective, you got a random result. Your partner on the other side of the universe also got a random result. Compare results, and that comparison travels at C or slower. The correlation appears. Entanglement doesn't transmit information, it transmits correlation. The correlation only becomes usable after classical communication at C or slower. Feynman. Take the math seriously. Don't use narrative shortcuts that make physics seem more intuitive than it is. Entanglement is real, but not a communication channel. C is intact. Causality is safe. But the universe has one more trick. If C limits everything moving through space, what happens when space itself is expanding? The universe is expanding. Not just galaxies moving through space, space itself is growing. Empty space gets bigger over time. This is the Hubble flow. Here's what breaks intuition. Far enough galaxies have space between us expanding faster than light speed. This doesn't violate relativity. Nothing moves through space faster than C. But the theory has no limit on how fast space itself expands. The Hubble constant is roughly 70 km/s per megaparsec. A megaparsec is about 3,250,000 260,000 light-years. For every megaparsec of distance, space expands 70 kilometers AS. At about 14 billion light-years away, the Hubble sphere space expands at exactly c. Beyond that, faster than c. Now think about the observable universe. The universe is 13 billion, 800 million years old. Intuitively, the observable universe should have a radius of 13 billion, 800 million light-years. That's how long lights had to reach us. But it's actually 46 billion light-years. Why? Light from distant regions traveled while space expanded. The light reaching us left regions now much farther than 13 billion, 800 million light-years because space itself expanded during the journey. Even more dramatic, the cosmic event horizon. We see galaxies right now whose light reached us, but they're so distant and receding so fast that their light today will never reach us. The space between us is expanding too fast. These galaxies send their final message, and we won't know it's the last. Over time, more and more galaxies cross this horizon. The observable universe keeps shrinking. Some regions of the universe are causally disconnected from us forever. CC, combined with space expansion, creates permanent information boundaries. Barriers no technology can cross, not because we're limited, but because of the universe's geometry itself. Feynman on scale. The human mind hasn't evolved to grasp cosmic size. We're looking at a universe with a 46 billion light-year radius, containing regions we'll never see or influence, with a past whose signals are permanently lost. CU isn't just a local speed limit. It's the architect of cosmic borders. C operates at every scale from GPS clocks to horizons where the universe closes off. But one question remains. Where does C come from? Why this number, not another? Here's the final breakthrough, the one promised at the start. What Feynman discovered about C at the deepest level. The answer rewrites everything. Feynman won the Nobel in 1965 for developing quantum electrodynamics, QED. It's the most accurate theory physics has. The electron's magnetic moment, a measurable property, verifiable in the lab, is predicted by QED to 12 decimal places. Experiments confirm all 12. This isn't coincidence. It's quantum mechanics and reality touching with surgical precision. And C emerges from this framework. QED's heart is the path integral formalism. This is where CQ gets truly strange. In classical physics, a particle traveling A to B takes one path. Least resistance. Newton's laws or space-time geometry. One path. In Feynman's QED, a particle photon, electron doesn't take one path. It takes all possible paths simultaneously. Every trajectory between A and B contributes to the probability amplitude of reaching B. Nearly classical paths reinforce each other. Wildly deviating paths cancel through interference. Observable behavior emerges from infinite quantum contributions. Among infinite paths are paths faster than Sako, slower than Sako, backward in time. Improbable loops. They all contribute amplitudes. For photons, paths closest to the classical path traveling at C reinforce each other most. Extremes cancel. What remains statistically is the path at CT. But CT isn't imposed from outside the photon. CT emerges as the dominant result when you sum all quantum contributions. It springs from quantum mechanics, not from above. The speed of light emerges from large-scale quantum summation. Feynman diagrams have objects called virtual photons. They're not real particles, never directly detected. They're mathematical intermediaries. They travel at any speed, faster or slower than c. Because they're off-shell, outside the energy-momentum relationship real particles obey. Real photons, the ones you detect, travel at c key. Virtual photons don't. What separates real from virtual is being on-shell, satisfying the relationship, guaranteeing they're propagable and detectable. Feynman. Physicists don't truly understand what a photon is. He said this as QED's creator, not modesty's scientific precision. QED describes photon behavior with extraordinary precision. But what a photon is at the deepest level, what taking all paths simultaneously means for reality, remains one of physics's most open questions. Feynman revealed, key is what emerges when quantum mechanics' infinite paths Interferences, virtual particles, amplitudes, sums up on a large scale. C isn't imposed from outside. C springs from within. Remember that paradox? Now the picture's complete. So what did C break? It broke time. Time isn't universal. It runs differently depending on speed and gravity. You use this every time GPS finds you. It broke space. Length contracts with motion. Now isn't universal. It's relative to each observer. The light cone defines what can influence what. It broke mass and energy apart. They're the same thing. C2 is the exchange rate, allowing stars to shine for billions of years. It broke the idea that quantum mechanics challenges C. Entanglement is real and verified, but it doesn't transmit information. C remains intact. Causality survives. It broke the universe into regions. Some parts of the cosmos will never see or influence because of space expansion combined with C's limit. And finally, the last and most unexpected break, it rewrote what C actually is. Not an external limit. It emerges when quantum mechanics sums all paths and extremes cancel through interference. C isn't a rule the universe obeys. It's the universe describing itself. The first 6 breaks revealed what C does. This last one reveals what C is. Feynman left more than equations. He left an attitude. Take experimental results seriously, even when they offend intuition. Resist explanations that feel right but don't match the math. Accept that the universe is more structured, coherent, and bizarre than our brains evolved to intuitively grasp. CE isn't a frustrating ceiling limiting what we achieve. It's the signature of a cosmos with architecture. Time and space are relative. Mass and energy are interchangeable. Causality has a maximum speed because without it the universe would contradict itself. This maximum speed springs from quantum mechanics as an emergent property of reality's fabric. Every time you use GPS, C is respected in every position calculation. Every time a star fuses hydrogen, C2 converts mass to light. Every time entangled particles are measured on opposite sides, C preserves causality without forbidding quantum correlation. Silently, the entire universe runs on a single number. If Feynman's mindset resonates, looking at the universe honestly, even when it refuses comfort, this channel will keep doing exactly that. Subscribe and follow along. 299,792,458 meters per second. Not a record to beat. The universe being exactly what it is.